Welcome my dear learners for this course on operations research. In this module 3 we were discussing on transportation problem. So far we have solved 3 problems on transportation problem. Moving ahead, the problem number 4 of our discussion on transportation problems states that ABC Limited has 3 production shops that supply a product to 5 warehouses. The cost of production varies from shop to shop and cost of transportation from one shop to a warehouse also varies. Each shop has specific production capacity and each warehouse has certain amount of requirements. The cost of transportation are given below. So we have shops ABC and warehouses 1, 2, 3, 4, 5 and we have supply and demand given. So it is a balanced transportation problem because sum of supply is equal to sum of demand. And also he has given the cost of manufacturing of the products in shop ABC. The variable cost and fixed cost are specified. Find the optimum quantity to be supplied from each shop to different warehouse at the minimum total cost. So we want to determine what is the minimum total cost to transfer the quantities produced to warehouses. One careful observation to be made in this problem is he is also specified the manufacturing cost, that is variable cost and fixed cost. Whenever we have the variable cost and fixed cost, always the variable cost should be considered in the transportation matrix and then solved. So therefore add the variable cost to the respective transportation matrix and then take it as the initial transportation matrix and then solve. Come, let us solve this problem number 4. So if we move on to solve problem number 4, the fixed cost has nothing to do with because it is fixed amount. Whatever path you trace to transfer the products from shops A to warehouses, it doesn't make any difference. But variable cost make difference. So therefore this variable cost should be considered in the transportation matrix. So in solution, fixed cost has nothing to do in transportation matrix, has no effect on transportation. Consider only variable cost and then solve. That's why he has asked to find what is the minimum total cost. He has not asked what is the minimum transportation cost. Kindly make a note. So now the new transportation matrix will become, we have shops A, B, C, and so the new transportation matrix will become, we have the shops A, B and C, and we have the warehouses 1, 2, 3, 4 and 5. So for shop A the variable cost is 14, so therefore for shop A I should add 14 to all the values. So if I add 14 plus 6 is 20, 14 plus 4 is 18, 14 plus 4 is 18, then we have 14 plus 7 is 21, then we have 14 plus 5 is 19. Next for shop B we have the variable cost as 16, so add this 16 to shop B. So 5 plus 16 is 21, then we have 6 plus 16 is 22, then we have 7 plus 16 as 23, then we have 4 plus 16 that is 20, finally we have 8 plus 16 that is 24. Then we have for shop C the variable cost is 15, so add it to the shop C, that is 15 plus 3 is 18, 15 plus 3 is 18, 15 plus 4 is 19, then we have 15 plus 6 as 21, 15 plus 3 is 18, 15 plus 4 is 19. Done. So for this transportation matrix we should solve for the demand of, so we have the demand demand is 60, 80, 85, 105 and 70. Coming for supply is 100, then we have 125, then we have 175. The sum is yielding to 400. Let me cross verify. 225 plus 175. Yes, it is 400. Here we have 60 plus 80 plus 85 plus 105 plus 70. That is also 400. So this is our required transportation matrix. So for this transportation matrix, we should solve. So now if I solve this, I will get the initial basic feasible solution. To find the minimum total cost, I should check for optimality, that is by using modified distribution method, that is UV rule. Now since he has not specified which rule to be employed to obtain the initial basic feasible solution, by default let us go with VAM, that is Vogel's approximation method, which is the fastest to obtain the optimality. So therefore I will go with VAM for the initial basic feasible solution. Come, let us solve the initial step 1 by using VAM method. Now moving ahead to solve for initial basic feasible solution by Vogel's approximation method. So first let me calculate the penalty. Penalty for minimization problem, minimum transportation problem, is defined as the difference between the least cost and next least cost in the corresponding row or column, right? So therefore let me calculate penalties. Let me calculate penalties in each step. Similarly, let me calculate penalties here also. Penalties for step 1, 2, 3, 4, if necessary 5. Now the least cost here is 18 and the next least cost is 19, so penalty will be 1. In this row the least cost is 20 and the next least cost is 21, so penalty will be 1. The least cost is 18 and the next least cost is 19, so penalty will be 1. So if I come here in the column, the least cost is 18 and the next least cost is 20, so penalty will be 2. Least cost is 18 and 19, penalty will be 1. Here we have 18 and 21, penalty will be 3. Here we have 18 and 20, so penalty will be 2. Here we have 19 and 24, penalty will be 5. Penalty will be 5, so therefore I should go with this one, which has highest penalty. So here the minimum cost we have is 19, we have 2, arbitrarily we can break. So let me go with one which has highest allocation. So 175 has highest allocation, so I'll go with this one. So for this cell I should take minimum of 70 and 175. Minimum is 70, so this is removed, so I cannot allocate here and here. Since I removed 70, the left out is 105. I left out with 105. You can go here also, that is also correct, no worries. Next I'll go for second step and calculate the penalties. So now least cost is 18, next least cost is 20, penalty is 2. Least cost is 20, next least cost is 21, penalty is 1. Least cost is 18, next is 19, so difference is 1. So we go for column, least is 20, next least is 18, penalty is 2. Here we have 18 and 19, penalty is 1. Here we have 18 and 21, penalty is 3. Here we have 18 and 20, penalty is 2. So this has no allocation left out. So therefore in the second step the highest penalty is 3. So here the least cost is 18. So for this cell I should check the minimum of 85 and 100. So 85 is minimum, so I cannot do any allocation here, so this is ruled out. So I removed 85 from 100, I left out with 15. Next go for step 3. Least cost is 18 and next is 20, penalty is 2. Least is 20 and 21, penalty is 1. Here we have 18 and 19, penalty is 1. So coming for column, we have 18 and 20, penalty is 2. Here we have 19 and 18, penalty is 1. So we have done with this column. Here we have 18 and 20, penalty is 2. We are done with this column. So now the second step, the highest penalty is 2. So we'll go with this one. If I go with this one, so we have the least cost is 18. I can allocate only 15 here. I can allocate only 15 here. So let me allocate only 15 here. So if I allocate 15, I left out with 65. I left out with 65. So since 15 is done, I cannot do any allocations in these two. Next, let me go for next step. So this is done. Here the difference will be 20 and 21 is 1. Next we have 18 and 19 as 1. Here we have 2. Here we have 19 and 22 is 3. 19 and 22 is 3. This is done. Here we have 18 and 20 as 2, and this is done. So since 3 is the next highest penalty, so therefore I should go here. So I have 65 and 105. Let me put 65 here. So and I left out with, if I put 65, I left out with 105 minus 65 is 40. 40. So since there is no allocation left out, so this is also done. Now if I go for next step penalty calculation, we have penalty as 1. Here we have penalty as 0, 18 and 18. Here we have penalty as 2. This is done. This is also done. Here we have penalty as 2, and this is also done. So we have highest penalty as 2. I will go with this one. So 60. So 18 is the minimum. So minimum of 60 and 40 is 40. So this is done. So I left out with 20. So only this box is left out for 20. There is no choice. So hence I should put 20 here only. There is no choice. If I put 20, I left out with 105. So only one box is left out for 105. I will put 105. That completes the Vogel's approximation method. Now if I calculate the allocation as 15 plus 85 plus 20 plus 105 plus 40 plus 65 plus 70, which is 400. So we have done the allocation using Vogel's approximation method. So this is our initial basic feasible solution. Now the initial basic feasible solution is giving us the total cost as the total cost is found to be 18 into 15 plus 18 into 85 plus 21 into 20 plus 20 into 105 plus 18 into 40 plus 19 into 65 plus 19 into 70. So this will yield us 18 into 15 plus 18 into 85 plus 21 into 20 plus 20 into 105 plus 18 into 40 plus 19 into 65 plus 19 into 70, which is equal to 7605, which is equal to 7605. 605 units. He has not given the unit of cost. I got the answer as, let me take it in rupees. If I consider it in rupees, we have got the total cost as 7,605 for the initial basic feasible solution. Now the number of allocations is 1, 2, 3, 4, 5, 6, 7. We have 7 allocations, whereas we have 3 rows and 5 columns. So m plus n minus 1, number of rows plus number of columns minus 1. Number of rows is 3, number of columns is 5. 5 plus 3 is 8 minus 1 is 7. The number of allocations are also equal to 7. So therefore it is a non-degenerate basic feasible solution. So since number of allocation is equal to 7, which is equal to m plus n minus 1. That is 3 plus 5 minus 1, that is also 7. 3 rows, 5 columns, minus 1 is also 7. Number of allocation is also 7. This is a non-degenerate basic feasible solution, and the total cost is found to be 7,605. Now let us go for step 2 to check for optimality by using Modi method. Let me pause this video for a while so that people can copy it down. Later we'll go for optimality test. Now moving ahead for optimality test, that is step 2 optimality test. I'll be using modified distribution method, that is UV rule. Now let me rewrite the same matrix again. We have, so I want to find U's and V's, right? So we have V's, V1, so 20, 21, 18, then we have 18, 22, 19, then we have 18, 23, 21, 21, 20, 18, then we have 19, 24 and 19, right? So this is the cost what we have. (21, 22, 23, 20, 24, 18, 19, 21, 18, 19, right? And we have the allocations of 15, 85, 20, 105, 40, 65 and 70. Now to start with, always, you already know that always start by giving U1 as 0. Since U1 is 0, we have allocation here, so I can find the value of V2 and V3, V4, V5. So what is the rule? Let me recall. So we have a rule that for allocated cell, cost Cij is equal to Ui plus Vj. Find Ui or Vj. Find whatever is required. For unallocated cell, find the penalty. Penalty is equal to cost Cij minus Ui minus Vj. right? Now for allocated cell, I have u1 is 0. Since we have allocation, cost is 18, v2 should be 18. Here I have allocation, cost is 18, v3 should be 18. Next, so we know v2, here we have the allocation, so therefore cost is 19, v2 is 18, so therefore u3 should be 1. 18 plus 1 is 19. Since I found u3, here I have allocation, cost is 18, so v1 should be 17. 17 plus 1 is 18. Here I have allocation, u3 is known, cost is 19, u3 is 1, so v5 should be 18 plus 1 is 19. Next, since v1 is known, here I have allocation, so v1 is 17, cost is 21, remaining is 4. Since we have allocation here, cost is 20, v4 should be 16. 16 plus 4 is 20. So I calculated the values of u's and v's. Start with u1 is equal to 0, check for the allocated cell, find the values of v's. Then cross verify where we have allocation and one value is known. Here I have allocation as 65. Since cost is 19, v2 is known as 18, so therefore u3 should be 1. Since u3 is known, here I have allocation, v1 is calculated. Since v1 is known, here I have allocation, ut is calculated. Since ut is known, here I have allocation, v4 is calculated. Already u3 is known, here I have allocation, so hence v5 is also calculated. So this completes the values of u's and v's. For unallocated cell, find the penalty. That is, cost is 20, 20 minus 17 minus 0 is 3. Cost is 21, 21 minus 16 minus 0 is 5. Cost is 19, 19 minus 18 is plus 1. Cost is 22, 22 minus 22 is 0. Cost is 23, 23 minus 22 is plus 1. Cost is 24, 24 minus 22 is plus 2. Cost is 21, 21 minus 19 is plus 2 again, plus 2. 18 minus 17 is plus 1. So since all the values of penalties are greater than or equal to 0, the solution is optimum. So since all the penalties are greater than or equal to 0, the solution is optimum. The solution is optimum. So therefore the optimum allocation will be so this is the optimum allocation, and the optimum total cost, that is the minimum total cost, is also known for us. So therefore the optimum allocation will be, we have 20, 21 and 18. We have 18, 22, 19. Then we have 18, 23, 21. Then we have 21, 20 and 18. Then we have 19, 24 and 19. So this is the transportation cost for which we have found the optimum allocation also. So optimum allocation will be 15 and 85. 15 and 85. Then we have 20 and 105. 20 and 105. And 40, 65, 70. 40, 65 and 70. Which means that our initial basic feasible solution itself is the optimum solution what we got, and the minimum total cost is found to be the minimum total cost is equal to 7605, which we have calculated initially itself. Let me cross verify once again. 18 into 15 plus 18 into 85 plus 21 into 20, 21 into 20 plus 20 into 105 plus 18 into 40 plus 19 into 65 plus 19 into 70, 7605. So this is the total minimum cost and this is the optimum allocation what we have. This is how we should solve whenever, apart from the transportation cost, the manufacturing cost, specifying variable cost and fixed cost are given. Fixed cost has nothing to do with transportation cost, only variable costs will be affecting the transportation cost. So therefore add the variable cost in the corresponding row of the shops specified. For shop A it is 14, so add 14 for all the values in the shop A row, add 16 to all the values in the shop B row, add 15 to all the values in the shop 3 row. That will give us the actual required transportation matrix, for which we have found out the initial basic feasible solution using VAM, and we have found out that it is a non-degenerate basic feasible solution where the number of allocation is equal to m plus n minus 1 and the total cost was found to be 7605. Then we move to step 2 for optimality test using modified distribution method or UV rule. Since all the penalties what we have computed is greater than or equal to 0, the solution is optimum. If we have 0, which means that there is an alternate optimum solution, so using which I can also find the alternate allocation, but the answer will not change. This is the total minimum cost for the problem number 4. In our next lecture, I will take up a problem on degenerate basic feasible solution. How to solve degeneracy in transportation problem will be addressed in our next lecture. That's all from this lecture. Thank you all.